Friends, here's a recording from my class yesterday. We're discussing electromagnetic induction. And so I show circuits and how current can induce magnetic fields and how changing magnetic fields can induce current. So check it out, watch, don't forget to like, subscribe, and share. So first thing to start, this is the starting point. This is not even on the notes yet. This is like pre-notes. These are, again, super strong magnets. Mr. Lai and I keep these kind of hidden away because theoretically, they could mess up your devices. This device is called a galvanometer. Okay, it detects current. It measures current, very small currents mostly. Okay, so here's the question. This is not hooked up to any battery, nothing. There's no voltage source. But watch what happens when I move the magnet near the loop of wire. Okay, so what is happening here? We're getting current. There's current running through this. Again, no batteries, just from moving a magnet near the loop of wire. Okay, so that means I could have a magnet spinning near the loop of wire and you'd be getting current. Okay, or you can move the loop around the magnet and you get current. This is the basis of how you get electric power from moving things. If you build a wind turbine, great, you've got this like giant thing spinning up in the air. How do you generate electricity from that? Like this. Coil of wire, and it's got to be at least one loop. The more loops, the better. And then moving magnets, moving permanent magnets. Okay, that's the starting point. So we're starting by seeing that you can put it this way, changing magnetism or a changing magnetic field can generate current, can generate electricity. Place a magnet near a compass describe what happens to the needle. Compass, what do compasses do? Not necessarily. They don't necessarily show you directions. Why not? All right. Look, this compass, is this compass pointing north right now? No, it's pointing towards me. Why? Why is it not pointing in the direction we would normally call north right now? Because it's next to a magnet. So what do compasses actually do? They detect magnetic fields. Okay? The reason that a compass will point north if there's not another magnet in that round is because the Earth is a giant magnet. That's why. Okay. And how do magnets work? North is attracted to what? South. So if the north end of a magnet is attracted that way, then magnetically, what is that direction? Actually, south. Yeah. So what we call directional north is actually the south magnetic pole of the Earth. But we call it north because that's the direction that the north side of a magnet will point. Okay. Also, magnets, they're not permanent magnets. They can get messed up. So this particular compass is actually reversed. The polarity has reversed. And so the red end is actually the south end of this particular magnet. But regardless, let's take a look at what the magnetic field looks like around a magnet. Stuff sticking. So here's a magnet. As I go around, notice it points to the end, and then it's parallel to the magnet, and then it points to the end, parallel to the magnet on the side, and then points in at the end. So here's a magnet. I'm going to draw a perfect rectangle. Okay. And here's what the arrows look like. Again, that compass is a little bit messed up, but if it was pointing in the right direction, it would have looked like this. Pointing away from north, and pointing towards south. Again, one of the main points, compasses are magnetism detectors. They tell you about magnetic fields. That's what they do. We've seen that moving magnets can cause electric current. So now we want to see, can electric current cause magnetism? Does it go the other way? We call this induced current, by the way, right? This is induced current. It's induced by a magnet. So this is called electromagnetic induction. This is what's happening when there's a generator, right? Like I have a big generator at home. In the country, we lose power a lot. And so it's one that I like wheel out to the back of the house. I plug it in, this cord from the breaker box. And but what's happening is it's burning gas, it's running a gas motor, but that's just turning and spinning magnets and coils and stuff, and that generates electricity, right? That's how cars work. So a car will start, regular gas car will start with using some electricity from the battery, but then as the engine is running, it's recharging the battery. It does that through a device called the alternator, right? And again, how is it doing that? Through this stuff. The gas motor is running, so you put another belt on and it spins. You got magnets and currents, and that runs current back into the battery and recharges it. Okay, but now, so our hypothesis, here's the next thing we want to see. That current creates a magnetic field. So how do we create an experiment? First of all, how do we create current? We need two things, current, and we need to be able to detect magnetism. Okay, so we're going to create current using a circuit. And then we're going to use a compass to detect magnetism. Here's a little picture of what we're going to do. So we'll have a battery and then a coil of wire, basically going to create a short circuit. And then next to it, we'll have a compass. All right. So then if our hypothesis is correct, then the compass should move. Somehow it'll respond. Yeah. So this is a battery and a loop of wire, or a coil of wire. Here's what we've got. Bunch of batteries, and this thing is called a solenoid. This is one way of, well, we're going to see creating an electromagnet. It's just a wire wrapped around a tube. So it's a wire wrapped in a helix shape. You've heard of the double helix from the DNA stuff, right? A spiral staircase is actually the shape of a helix. It's not actually a spiral. Spirals get closer to the center as they go on, right? If spiral staircases were really spirals, you'd never make it to the second floor. So they're helix staircases. But nobody calls them helix staircases because people don't know what that is. Spiral sounds a little bit more poetic too. So anyway, but this has lots of loops of wire, which is good. The more loops there are, the better the effect. And I have my magnetism detector right here. Let that sit on top. This is a little tricky. There are a lot of magnets in this cabinet right here, so sometimes that messes with this. So watch what happens. I'm going to connect to the battery, and the compass responds. Disconnect. Again, I connect it, and you can see that compass is responding. By the way, I'm basically creating a short circuit. And now I take it apart, and the compass goes back. Okay. So what happens? That means what we just saw is that when we have current, we have magnetism. What I just created was an electromagnet. I had magnetism. I made a magnet out of that solenoid, but then I could just disconnect it and that turns it off. How many of you have had an MRI? Go in the MRI machine. Do you think they have just like giant magnets sitting in there? No. How do they create those magnetic fields? Right? Electromagnetism. They're running current through wires and creating an electric area, a magnetic field that way. So then what was the result? The compass moved. All right, so let me show you some applications of this right now. So let me show you this. When things break and they don't work anymore, you should take things apart and take a look. Did I show you the DVD player? All the things in the DVD player, the capacitors, resistors, all that stuff. Anyway, so this was a ceiling fan. Ceiling fan stopped working, so I replaced it. Right? Good to have some of these skills, by the way. Okay? I had to take the hacksaw out of this part, get it off. But watch. See how nicely that spins? That's the ceiling fan. This is where the ceiling fan attached. This is where the fan blade's attached, right? These wires that connected to the light housing. But anyway, what do you see in here? Lots of coils of wire. Why? Because when you run current through these wires, it generates a magnetic field. So this thing turns into a kind of a magnet with this complicated magnetic field. But then there are magnetic parts here in this in the ring around the outside, and that pulls on the magnetic field from the wires, pulls on the magnetic parts on the outside, and it pulls it around like that. Okay. This also was a stand fan in my house. You know the stand fans, they can like oscillate back and forth, and it stopped working. So what did I do? I took it apart. Wanted to see how it works on the inside. It's pretty cool. Again, what do you see? Lots of wire, coils of wire, runs current through this, creates a magnetic field, and then this thing spins. See, it spins kind of nice, but it stops. There's actually some resistance here because of this phenomenon. Changing magnetism creates current. Well, guess what? That current creates magnetism and actually pushes back. If it's just running like this, yeah. You probably have something that looks just like this in your house. If you have a fan in your house somewhere, it's like, that's what this is. You know, like a little stand fan, yeah. But here's the other thing too. This isn't just a short circuit. You couldn't run a short. It would overheat if it was just a short circuit. They've got it hooked up, and that's what engineers do. Is they look to see what's the right way to get the right amount of current, but still have not the wires aren't getting too hot, but you still want to have enough power. Anyway, all that kind of stuff. Take a look here. This is the piece, by the way. I just pulled this out, and if you look, this is magnetic material. There are little deposits of iron here in a certain pattern that can respond to the magnetic field created by these wires. Okay. There's another experiment, right? So here's the question. We've seen moving magnets create electric current, and we've seen electric current. Guys, listen. We've seen electric current create magnetism. So now, can current act like a magnet that then induces current in another wire that's not like connected to it or anything? Okay. So that's what we're gonna see if we can get to do. So here's the hypothesis. Current in one wire can electromagnetically induce current in another wire. So first of all, we need a way of creating current. So we've already seen how to do that. Right, I'm just going to draw a picture of it this time. So we've got a coil of wire. Right, so here's a battery. And actually what we're going to do, we're going to open and close that switch. And then another coil connected to the galvanometer to detect current to see if it works. Coils of wire, here's a switch. So we're going to open and close the switch. Because remember, we need changing magnetism. We need a changing magnetic field to create current. So prediction, galvanometer will move. Spelled like galvanometer. All right. So here's the galvanometer, and the galvanometer is coil of wire. And then here's this other coil of wire, and this is what I'm going to connect to the battery. The batteries. I'm going to short circuit this just to get enough current. Quickly connect and disconnect. Am I generating current as I connect and disconnect? Look at the galvanometer. Am I generating current? Yes, I am. Okay. This is how transformers work. This is how, so those two wires, they're not connected electrically, right? They're not connected metal to metal. But by changing the current in that one coil of wire, that's generating current in the other coil of wire. Okay. Again, this is all called electromagnetic induction. What are the results? Galvanometer moved. Electromagnetic induction works. Okay. This is the basis behind all electric motors, speakers, um, generators, any of those kinds of things. This is what's going on.